Today, we will discuss the fascinating uses of artificial intelligence at the world's most powerful particle collider, the Large Hadron Collider. What's up, you scholars of enlightenment? Dr. Sam Gregson, particle physicist here again. I hope you've had a brilliant start to the week. Now today, we're going to be discussing how scientists at the world's most cutting-edge particle physics experiments are using AI, artificial intelligence, to enhance their exploration of the subatomic world. Particle physicists are now leveraging the adaptive learning capabilities of AI to sift through, analyze, and interpret the colossal datasets generated by today's modern particle colliders. We are heading into a new era in particle physics, where the computational power of AI could allow us greater insight into the nature of our universe than ever before. To help me dig into the promises and pitfalls of artificial intelligence at the Large Hadron Collider, I'm joined by a phenomenal special guest, Dr. Oz Amram. Dr. Amram is a particle physicist at Fermilab and a member of the CMS collaboration at the Large Hadron Collider. Dr. Amram is particularly interested in ways in which machine learning can aid particle physics. His specific interests include model-independent searches for new physics, novel methods of calibrating exotic jets, and fast simulations of complex calorimeters using machine learning methods. He also regularly writes for Particle Bytes, which summarizes recent particle physics papers at the undergraduate level. Links are provided in the video description. So I couldn't hope for a better special guest to help me dig into the uses of artificial intelligence at the Large Hadron Collider. Okay, so Oz, thank you very much for agreeing to do this, first of all. And let's start right at the top. How would you define AI, artificial intelligence, and machine learning when it comes to particle physics? Are we talking about fancy statistics? Are we talking about classification? How would you define AI?
Yeah, I would define AI as any kind of system that learns from data, like from repeated examples. So there's definitely a blurry line between kind of advanced statistical models and an AI model. Yeah. But to me, they're kind of on a spectrum of just how complicated the model is really in practice.
And when we're talking about AI and machine learning, are we kind of using those interchangeably?
Yeah, I use them pretty interchangeably. I think different people have different opinions about it, but I use them pretty interchangeably for sure.
Good. We're not going to get lost in the nomenclature. That's good. So reading some of the publications coming out recently from the LHC, Large Hadron Collider, would it be fair to say that AI is becoming fairly ubiquitous in everything that particle physicists do over there these days?
Yeah, definitely. I would say so. So, the kind of AI is now in our kind of core of our kind of data analysis pipelines of like how we take these raw detector signals and figure out, oh, okay, there was a electron going this way and this is what its energy was, and a muon going that way. So now kind of there's, a series of steps we do that to go from those raw detector signals to this is kind of what we think happened in the event. And a lot of those have AI in them now. So that's just every kind of paper we put it out kind of just has AI in it at that level. But also on kind of like the broader level, I mean, the techniques that people are using now in data analysis, when you want to say, look for the Higgs boson decaying to two bottom quarks or something like that, the analysis techniques we use to analyze the data, like once we have all the objects, is very like heavily AI focused now. And it's, the main, I guess, bread and butter is this idea of classification. So a lot of the signals we're looking for are very, very rare. And we, have billions and billions of background collisions or collisions that we are not that interested in studying from processes that we've already studied well before. So we use the workhorse is these classification tasks where we kind of train an AI model to say, this is what a Higgs boson looks like. This is what the things that aren't Higgs boson looks like. Can you figure out how to differentiate them? And this is, has a long history in particle physics of using AI in this way. And it's just gotten more and more sophisticated and more powerful as we're using the modern tools. And so that's kind of the bread and butter. And I think what's been really exciting is now we're really starting to branch out into kind of more sophisticated uses of AI and figuring out other ways that it can really change how we do this kind of whole business that is particle physics experiments.
And we're going to get into some of those examples. You alluded to it there, but how established are these kind of AI approaches in particle physics? Because I've seen some sources that say, look, we've been doing this. This was the Javier Duarte's lovely talk at iChep recently, saying that we've been doing this since the 1980s, making sure that we find real tracks rather than fake tracks in our data. I've seen papers from the 1980s. I've seen Bruce Denny's tutorial on neural networks from the kind of early 1990s. How established are these techniques?
Yeah, so it is kind of remarkable going back and looking at these papers that people were kind of having the same ideas that we're having now, 30 years ago. And so there was kind of these initial kind of explorations back then in the late 80s, early 90s. But it kind of, I would say, wasn't super popular. It was kind of just like saying, hey, we could try to do this. Yeah. But a lot of the issue was the computational power wasn't there. So they're talking about neural networks, but they're talking about, things that we consider like would be so tiny compared to the type of models that we're training today. Yeah. They just didn't have the computational power to really get the kind of power you can get with something like a neural network. Yeah. So I would say that there wasn't much kind of direct usage of these AI techniques in the kind of particle experiment workflow until maybe the late 2000s or so. Like this idea of boosted decision trees became pretty popular. That's one type of AI model, kind of similar kind of intention to a neural network, but just a slightly different framework. And then the kind of rise of deep learning happened in the machine learning community starting, in around 2012 with AlexNet. And that kind of started to trickle into particle physics, essentially with a few-year time lag. So, convolutional neural networks were all the rage in, the machine learning world, and we ported them to particle physics starting in with a 3-year time delay. I think 2016 is when we started using them in particle physics. And now I would say particle physics is really, we're keeping up very closely with the cutting edge AI models. So if there's something new and that takes the AI community by storm and becomes really popular in a few months, there's a paper out. It's like using it so you have to be really quick at following the literature. But by the same token, there's stuff that the regular machine learning world isn't as interested in as us particle physics because we care about different things like trying to do some of these computations really fast, kind of on dedicated hardware, caring about uncertainties, and kind of different sorts of, our data has different kind of properties than, images. We have collections of particles which have different symmetries and stuff like that. And so we've also started to develop, our own tools that independent, kind of a different path of the regular mainstream AI stuff. So right now it is like kind of very interesting subfield within particle physics. It's like the kind of best uses of AI and where we can use it in our experiment.
I found that really interesting, that interplay between kind of the more raw AI field and then the applications in our field of particle physics, which then flow back into the community because we deal with specific types of data, very, very high dimensionality, sparse data in some places, very, very dense in other places. And that flow between the two, I think, is something I want to explore later when we talk about how we feed back into the community. But very, very interesting. Just before we move off this, when I was researching, it said, and I agree with you kind of on timelines, because I remember when I was doing my PhD around kind of 2014, people were really starting to, at the CERN tables talk about these things, but there wasn't a lot of, there were a few boosted decision trees and, but they've really come on over the kind of last decade. When I was researching, I saw some information saying that these boosted decision trees were essential for getting the significance to discover the Higgs back in 2012. Is that fair, or is that overselling it?
Yeah. So okay, I'm trying to remember the story off the top of my head, but the Higgs boson, we discovered it by combining different channels, and one of the golden channels was the Higgs decaying to 2 photons because that could leave a very clean signature in our detector. And I'm pretty sure that initial discovery then was using a boosted decision tree to help identify photons with the highest quality we can. And so I don't remember exactly how much it was boosting your significance as compared to a classical one, but I think it was, part of the analysis. So I would imagine that it was giving some gain.
It's a nice little story for the AI heads to use anyway. Okay.
Yeah. I mean, it's whenever we can point to say, hey, we discovered something because of AI. It's a nice thing to be able to do.
Exactly right. So just before we get into some of the specific uses, so we've kind of alluded to this a little bit, but why do we need these AI approaches in particle physics? What are the major benefits of using AI and deep learning over more traditional methods? Is this about the amount of data, the dimensionality of the data? What are the huge advantages that we get from taking these new approaches?
Yeah, it's definitely both. It's that our data is very high dimensional and complicated, and there's lots of hidden correlations that it's really difficult for us as physicists to understand at the kind of, what's interesting actually about physics is that we did a pretty good job before AI. And essentially, like, if you compare us to the machine learning world where they're trying to classify images of cats versus dogs, essentially they can't do that at all without AI, right? But we as physicists, we had a pretty good understanding of, this particle looks like that particle looks like this. And we came up with these rule-based algorithms and we did okay.
And this is what I kind of remember from when I was doing my PhD is, look, I'm looking for a particular decay channel. Well, it probably has a couple of tracks with, momentum above this, and it probably has a mass kind of like this. And, if it's a muon, it probably has some hits in the muon chain. And if it's this kind of particle, it probably shows this amount of Cherenkov light in the other detector. So we kind of did these correlations and these interactions between different pieces of data with kind of experience and our intelligence, but obviously we can't. It's very hard to optimize. In that high dimension.
So right now, I would say a lot of the data analysis, it's doing a mix of that because, I mean, you try to optimize it the best you can, but you do try to use like kind of human understandable selections that you're applying to your data in addition to AI. Because if you just shoved all of your kind of data into the AI and got an answer out, that's not always the most satisfying. And also you have to, make sure the AI is really doing, you have to be able to trust it and make sure it's doing exactly what you want. So in terms of why we need AI, there are many kind of things we want to do in particle physics where the intrinsic dimensionality is very, very high. I mean, if you think about our detector signal, we have, if you take at its lowest level of like how many individual readout cells are there in our detectors, I mean, it's millions and millions. So having a human that can kind of, understand all of those and do the perfect algorithm to do those things is kind of not possible. So that's
40 million times a second as well, and over.
So that's the other thing is we have to do a lot of these data analysis techniques when we sometimes in real time. So and that's actually a very exciting area is applying AI to these real time decision makings where you have to the AI has to make a decision 40 million times a second. And it's only recently that kind of particle physicists have kind of helped develop the technology that enables those kind of applications. So that didn't really exist in industry before because most industry applications don't have to run 40 million times a second.
I don't need to know if it's a cat or 1 second delay for knowing whether it's a cat or a dog is usually going to be okay.
Exactly.
That's not going to work for our 40 million collisions a second or whatever it might be.
Yeah, exactly. So that's a really exciting development of this kind of real-time fast AI. And then we're seeing that, once we kind of develop those tools, they are getting usage in other scientific domains and in industries. Once you build something, people realize that they can use it too.
Okay, so we have a hell of a lot of data. It's very, very high dimensionality, and we want to have greater efficiency in filtering that, understanding it, better signal to noise, all these kind of things. So AI clearly very, very applicable and very, very important in particle physics. So let's jump into some of the specific use cases. So you talked about improved classification, and I know one of the things that you work on, I've got a couple of examples, is jets. So can you tell us a little bit about how AI can help us deal with jets? Basically what a jet is and why it's difficult to deal with normally.
So jets have been kind of like one of the golden use cases for AI and particle physics. and have kind of driven a lot of the developments of new techniques. So jets, at a physics level, are these sprays of particles that come out from our detector, or from the kind of interaction point. So when you produce a particle like a quark, so a quark is the thing that's inside protons and inside neutrons, and they have this really interesting property called confinement, which essentially means that you never see a quark on its own. Yeah. So if you do produce a quark on its own in the initial collision, as it is kind of traveling to the detector, it's going to kind of spontaneously create other quark-antiquark pairs out of the vacuum, so it can kind of bind to them and not live on its own. Yeah. And then essentially this results in a huge shower of particles. So you start with one particle at the collision point, and by the time it reaches any sort of detector, probably you can have 50 to 100 particles that you're measuring, and so you end up with this spray that we're called and the spray is called the jet. Yeah. And a lot of times we want to use the properties of this jet to infer, okay, what were the properties of the initial quark that produces, because that's what we normally care about, like what happened in that real collision. Yeah. So what is the energy of that quark, and what kind of and can we classify it? Was it a quark? Was it bottom quark, which is one type of quark, or was it another type of quark or something like that? And this is something we really care about, particularly when studying the Higgs boson. Yeah. So the Higgs boson loves to decay into bottom quarks. It's its like favorite channel. Yeah. And for a long time, people thought, okay, that may be the channel it most often decays to, but you're never going to see it at the LHC because there's so many jets already. Yeah. Like the LHC is smashing protons together. A lot of times you just get quarks and the protons coming out. Those produce lots of jets. That looks very, very similar to the Higgs boson you're trying to see. So people thought when they were designing the LHC, okay, yeah, you won't be able to see it in that bottom quark channel. You'll have to look at the photon decays or the leptonic decays, which happen 50 times less often or something than the bottom quark ones, but just because it's a cleaner signature. Yeah. Yeah. But really, what's happened with machine learning is we've gotten really good at kind of analyzing jets and determining what their properties are, and specifically trying to identify what their origin was. So identify if they came from a B quark. And that is a problem that's really great for machine learning, because you have, the jet is made of 50 particles. Each of them have, a direction and energy. So you're talking about, a couple hundred dimensional thing that is the jet. And you can, even consider, additional properties of each particle, like how displaced it is from the interaction point, like how much kind of it traveled before decaying, or how nice the track looks in our detector. So you can it can get very, very high dimensional very quickly if you want to use all the information possible. Yeah. And so this has really been kind of one of the drivers, a lot of machine learning in our field. And it started with very simple kind of algorithms that we could understand, and then using boost decision trees. And now we're using the fancy things like graph neural networks and transformers and stuff. And we see the performance just keeps getting better as we use more and more sophisticated tools. Yeah. So this is a nice plot from the Atlas experiment. And so, if they're kind of referencing how much better we are at identifying these bottom quarks as compared to their baseline was 2017. There's already a deep learning algorithm. This DL here stands for deep learning 1. And so now we're in 2023, and we're using these graph neural networks, which are giving us essentially 4 times better performance. So essentially for a fixed value of how often you can identify a B quark, you will have 4 times less background, which is like a huge gain for us. And essentially, this has allowed us to really study this Higgs boson decay to bottom quarks at like much greater precision than we ever thought we would when we designed the LHC. And then it allows us to do other things. We can go analyze jets and look for kind of different sorts of jets as well. So this plot is from a recent search from CMS that's looking for kind of jets that have a different property than normal quarks. That would be the indication of a new particle. So sometimes you can have 2 quarks inside a jet. So if you have, like, for example, a Z boson or a Higgs boson, and if it's produced with a lot of momentum, when it decays into 2 quarks, they'll both end up inside the jet. And so that jet, even though on its surface level it just looks like a spray of particle, it will have this characteristic that there'll be kind of two axes along the jet in which a lot of the energy is distributed coming from those two quarks. So it's kind of like two showers overlap in one. And so this is a search looking for new kind of particles that would produce this sort of jet. And what's nice is that, okay, there is some stuff in the standard model, like the Z boson can decay to two quarks or to two B quarks. And they can see that in the search. And people did not think it would be possible to ever study something like the Z boson decay to two bottom quarks of the LHC. So this is really kind of, been a bit of great journey of kind of new techniques, kind of continuing to give gains in performance. And everyone keeps thinking that, okay, now we've really reached the limit, that we're not going to be able to do any better. There might be a fundamental limitation to how well you can separate these two things.
Yeah.
But then the next thing comes along and it's even better. And so, we don't know how long we'll keep
it's
going,
it's really hard
impressive
for us to know, right? Because you talk about this massive dimensionality, like you said, 50, 100 particles or whatever it is, all with these number of tags. It's hard for us to even kind of get our mind around what might be possible. So
exactly. We don't know of any theoretical limit, but we just kind of had an intuition that, okay, at some point, you won't be able to do any better, but it keeps doing better.
So because we can do a lot better with these jets, I guess we can also go looking for signals of new physics with jets or other things like this as well. So a lot of decays that would have been invisible because they're just lost in the mess of the hadronic background, like you said, we can now look at. I think we've got an example of that actually. I think there's a beyond standard model search for, see if I can find it. Or maybe it is this one, which was, I think this might have been actually, was it?
This is a beyond the standard model search. They just have a nice kind of example of that there is also a Z boson there. So the left plot is comparing essentially the search we did, I want to say 2017 or so, and what things look like there. And then if you compare to the plot on the right, this peak of the Z boson in the blue is much more visible now. So we're much better at identifying it than this. And so that means that we have much greater sensitivity to any new particles that would have looked kind of similar to that. And okay, in this search, we didn't happen to see any, but we're really increasing kind of the chance that we could actually find something by increasing sensitivity.
So we're really able to drag out. I mean, if we look here, we've got what number of events? There's 1,000 here. We've gone up a kind of factor of 10, and we've got a much bigger peak over the background as well, which both of which work in our favor.
Another flagship example of this is actually one of kind of the goals in all of particle physics right now is that, okay, we've measured the Higgs boson, and a really important property of the Higgs boson is how much it interacts with itself. Because this determines the shape of what's called the Higgs potential, which is essentially the shape that we care about for this story of how everything got mass in the universe. It also can determine, is the universe fundamentally stable, or is it going to decay in billions and billions of years to some other state or something like that. So there's a really central question in particle physics. And initially people thought, okay, maybe by the end of the LHC run in like 2040, we might just have evidence that we can see this interaction between two Higgs bosons. And essentially, because of the rise of machine learning and our really greatly improved jet classification performance, we're hopeful that by the end of this current run, so maybe in 2026 or 2027 or something, we'll actually might have evidence of this interaction already.
Wow.
So that's not a guarantee, but it's like given the rate of improvement, we're beating expectations by like factors of 10 and stuff. So we really have done a lot, and this is kind of one of the most central questions in particle physics right now. That is going to be, that machine learning is going to play a large role in it.
And this is a question that people think will only be answered with an FCCEE or future collider, but you're saying we might be able to get hints and see some of these multiple Higgs interactions potentially by the end of the decade if we continue to improve in these machine learning. Very interesting.
I think so.
Awesome. So classification is very, very important. We need to be able to understand what we're seeing. We need to be able to drive down backgrounds and increase our signal. Another region where this comes in, and I know you've done some work in this area as well, is simulation and modeling. So AI seems to be showing up in particle physics a lot in the rapid creation of simulated data. So what's going on here? Because I think a lot of people don't really realize, but when we find some results in particle physics, we want to make sure that we could simulate those and we could create the same plots essentially from scratch. Do we understand the physics that's going on? Sometimes we even simulate them ahead of time so that we can get the rough shapes of various things that might go into the fits of data. So we need, after we've found these things, to be able to reproduce them from physics that we understand in simulation. Why is that such a big problem, and how can AI help us with that effort of simulation?
Yeah, so definitely, so simulation is like a really crucial aspect of how we analyze data from these experiments. Essentially, you're getting all this data in, you want to make sense of it, you want to compare to things you know about, like, okay, does the Higgs boson look like how I expect? Well, one thing I can do is simulate how the Higgs boson should look if it behaves like I expect, and compare that to the data I observed.
Exactly.
And so essentially so we simulate many more events than we actually record from the collisions, because you just want to reduce statistical uncertainties on the simulations as much as you can. And as you know, we're collecting tons of data. That means tons of simulations that have to be performed. And essentially, we expect that once we kind of increase our data taking rates after this high luminosity upgrade, that's going to essentially, the LHC is running now on what's called run 3, but then it will shut down for a few years and will increase the intensity of the beams so that we get more collisions and more data.
We can see kind of in these plots the number of kind of tracks that have gone.
Yeah, exactly. It's really striking. Like there's going to be 200 kind of average interactions happening at once, and then we have to disentangle all of that. So that's a huge computation.
This scares an old LHCb guy. Like, there's no, none of this. Anyway, I'll part that.
So we would like that when we have these, increased data volumes, we can also, run a comparable number of simulations, so we can compare the data that we're seeing. But we're expecting that if we kind of use the classic, simulation chain that we have been doing, which simulates each step of the process based on the, fundamental physics of how these particles interact with our detector and everything, we're just not going to have the computing resources to be able to do that. And so the idea is, since I want to say, when was Pascal? So I was trying to think when the first proposal, this was maybe 2018, was, hey, what if we replace this, physics-based simulation with a machine learning model that can kind of mimic it?
So just to for people who are watching to understand, essentially, to do this simulation, you have to generate the particles, you have to fly them through the detector, you have to model the detector, model the interactions of those particles with the detector. What will the detector do when the particles hit them? Will it make more particles? Then you have to trace all of those particles through the detector, how they interact, more particles. And it becomes very, very difficult. You're essentially recreating particle collisions and how these particles fly through your detector and interact. So it becomes incredibly taxing and incredibly computationally demanding very, very quickly.
Yeah, exactly. So the idea is, okay, there's all these great tools in the machine learning world for generating, artificial images. Like, if you've seen DALL-E and stuff, have gotten really popular recently. But they've existed for a while in slightly different versions. So could we replace our, physics-based detector simulations with one of these AI models so that essentially, and the AI model can run much faster. And so what we do is we train our AI model on the real physics-based simulation. So we do generate a bunch of simulations, and then you tell the AI model, hey, go copy what this physics-based simulation is doing. And then
getting all those correlations and all those interactions between how many hits happen if it's got this energy, or if it goes over here, where do we see hits in the detector, and all these kind of dependencies between the data.
So what we want is, you give a machine learning model, I have an electron of this momentum hitting this part of my detector. What does that look like? And then it would generate kind of the image of what that would look like. It would be the goal. And so this is something that's been worked on in the kind of machine learning plus particle physics community for the last several years, and we've gotten pretty good at it now. So Atlas, one of the major experiments at the LHC, is actually using these machine learning models in their about 50% of their simulations that they're producing right now.
Wow.
Is using this fast GAN. So GAN is a type of these machine learning model. And essentially, they had a first version of this a few years ago, and it kind of showed that it could work, but it wasn't quite at the level of accuracy that we needed. But they've generally improved it, and now it's really it's not quite. We still know that there's some small residual differences between the true physics-based simulation and what the AI model was giving us, but it's at the level where we can account for that in most data analysis that we're doing. And
I think they said they do an additional step on top as well. These adversarial neural networks, where you have one that's kind of trained on the full simulation, and if the other one looks too far different, it goes kind of smacks it down and.
So this general architecture of a generative adversarial network is GAN. It was like kind of the most popular kind of what's called generative model, or something that can make a new image or detector signal for a long time. And it has exactly this structure where you're training a model that's trying to kind of mimic match what the physics-based simulation is doing, and then you train another model that's its adversary. So that model takes in, okay, this is the simulation that the physics-based thing produced, and this is one that the other AI model produced. Can I tell them apart? And essentially, then that will tell the AI model, hey, I can tell your simulation is different because you keep getting the electron shower in this region wrong. So go fix that, and then that model will try to fix that. And so it's kind of this back and forth game between these two, and so that can work really well. Eventually, those two models the model will say, I can't tell them apart anymore because it's really doing a very good job simulating it.
So instead,
of course, that's not.
Sorry, please.
That's not the end of the story. We do lots of other validation to make sure that the thing we're actually ending up with is giving us good physics results. And there's some additional, post hoc corrections through small fixes and stuff like that. But on the whole, we're doing a pretty good job of it. And in CMS, we want to move in this direction as well. It was actually a more pressing need for Atlas because they have a more one of their parts of their detector was a little bit more computationally expensive to simulate than CMS's was. So they really needed this now. And so they have it employed now. And CMS, we're thinking for this high luminosity upgrade is that when we'll kind of move to this approach.
Amazing. So instead of tracking every single electron or whatever it might be through the detector, we can say, look, an electron has arrived at cell number 8472, and we know exactly what that looks like. Usually we know what it looks like depending on the energy that arrives. Make me that picture. And we can cut out that entire simulation step essentially and use the much quicker AI model. Very, very interesting. Yeah. Very, very cool, particularly as we go up to these high luminosities. And as you said, these are very, very good. So over very different energies. So I think they've got a shower energy of 4 GeV, and then more than 250 GeV over here. Pretty good. Yeah. Pretty good. Like you say, little residual differences between the simulation and the AI model, but on the whole, very, very good. So excellent kind of performance.
And so this plot is it's funny. So I think the publication process for this paper from Atlas took several years. So though this plot was public now, I think it's actually a few years behind the current state of the art in this machine learning simulation of particle physics stuff that people have been working on. So I think it's actually probably the state of the art has probably improved a little bit even compared to this. But yeah, we've gone pretty good at it, I would say.
We're always lagging behind intense peer review, so we have to be careful what we can show. Excellent. Yeah. Good to hear. So I want to move on to another one, which I know, and this is kind of where I became aware of the work that you were doing, which is the idea, and I think a lot of people will really be interested in this section, is the idea of anomaly detection. So using these pattern recognition algorithms to look for anomalous signals in the data, and essentially the idea of, can we find new particles, or can AI, when I can speak, find new particles on its own? So what's the idea here? Because I guess with a kind of supervised learning, usually you're telling it exactly what to look for, but maybe this is unsupervised learning. So I'll let you run with that.
Yeah, exactly. So as we've been talking about, we've done a lot of these classification tasks with AI, and we normally have to tell the AI, hey, this is what a Higgs boson looks like. so we can train it, give it some examples of what Higgs boson looks like, and then we can go look in our data and see, can it find Higgs bosons, and you can do that with new particles.
Oh,
like,
my dark matter looks like this.
Yes,
I think.
yes, exactly.
Can you see anything that looks like that in our detector? Maybe. Yeah.
But we know that kind of the space of possibilities of what new particles could live in our data is like bigger than the time we have the bigger kind of than we have the human resources to do like a search for each one of them. So train an AI model to look for this version of dark matter and that version of dark matter. So we know that space is bigger, and we also just kind of want the ability for our data to surprise us, right? There could be something in our data that we haven't thought of yet, and we want to be able to discover that. Like it would be real shame if we missed some discovery that was living in LHC data just because we hadn't thought of the right thing to go look for. There's so many famous stories in science of unexpected discoveries and stuff, and that's very difficult in a super complex environment like the LHC, where you have billions of collisions to look through that 99.999% of them are background events you don't care about. The data is very high dimensional, so that's why we kind of have these traditional strategies of looking for one particle at a time. And so what we're doing now with machine learning is this idea of anomaly detection is, can we let the AI model kind of find anything anomalous in the data? So and there's a few different ways to formulate that problem, but one of them is you train it on all the regular data where there's no new particles in it, and it kind of learns what typical LHC events look like, and then you have it go look somewhere else and say, is there anything that looks dissimilar to what you've seen before? And that is an indication that it might be a new particle that produced that collision, because the collision looks very different than anything the AI had seen before. And so in that way, you can kind of look for many types of new particles at once, hopefully, because lots of things would look different than what the AI is trying. So you have this idea. We talk about the idea of model independence. So the AI would be sensitive to many different models of new particles and stuff like that.
So you're just saying, don't go look for this specific decay of X to dark photons or whatever it is. You're saying, look, just go look at the data and tell me if you find anything that looks weird relative to.
To exactly. So I've pitched this before as, it's AI-led search. Instead of us telling the AI what to go look for this dark matter or that dark matter or whatever, you just give the AI the data and let it tell you what it thinks is interesting and anomalous. So yeah, for the first time in CMS, we did a search using this strategy. And this kind of middle step of, okay, how do we let the AI tell us what is anomalous? There's no one right answer to that. If you don't know exactly what you're looking for, it's hard to say this is the best thing to do or that's the best thing to do. So we had several different strategies, but they all kind of fit within a same framework of, we take some data, we run it through the AI and let the AI tell us what is the most kind of potentially anomalous looking of these events in that data, and then we analyze that with some statistical methods to determine are there any signs of new particles in those kind of anomalous?
So when you did that, I've seen it explained kind of, you kind of take the data, digitize it, turn it into an image essentially, and then try to recreate it. And if you get a lot of loss between what you put in and what came out, then these are probably the rarest events. How exactly did that kind of step work? How did you assess kind of weirdness, if you will?
Yeah, so one of the strategies worked very similar to what you're talking about. So that's a type of neural network that's called an autoencoder.
Okay.
And so you want to be able to kind of encode how weird does this thing look. And one way to do that is this compression task. So you take in some representation of your data, like an image or something like that, and the model is trained to compress that down into some smaller kind of compressed, representation, like you use them when you're zipping a file or something like that, and then decompress to recover the original thing.
Right.
And there's going to be some amount of information loss because you compressed it down, but the model will do the best it can to preserve the original thing. So you take that model and you train it on some, examples from your data where you're pretty sure that there's no new signals living in them because you have some physics-based knowledge of that. It'd be very weird for a signal to show up there. And then so this model learns how to do this compression, decompression task on kind of normal standard model background events. And then you go take that model and you go to another part of the data where you think there might actually be signal, and you run everything through this compression decompression task, and then everything that comes out looking kind of where there's a big difference between the original and the uncompressed version, then you think that where the model's not doing a good job of compressing it and recovering the original, that thing is probably dissimilar to any type of event it has seen before that was in its training set. And so that's a good indication that that type of event is looking a little bit different than a normal type of collision, which we expect to be good at. So that was one.
And then you can go look in those events and see if there's a bump or a wiggle or something in your data.
Exactly. That's what we did. So that's one method of how you kind of look for anomalies in the data, where it kind of, you just learn about the background and then you look for everything that looks dissimilar to the background. There's these other methods which kind of can work in a different way, where they kind of find clusters of events that don't exist in the background. So you have some example, you look in some region of the data and you ask your machine learning model, is there any difference between the data over here and the data over there, where you expect that essentially if there's no new particles, the data in those two places should be the same. And that AI model will actually learn to identify the specific characteristics of the signal if they live in that little window. Because if there was a cluster of signal events, it would kind of see that, oh, there's a bunch of events over here that have jets that look like this, where the jets over there always look like that. Yeah. And then it can tell those two things apart. So that is kind of another philosophy of how you look for these anomalies, where you're kind of trying to tell apart these two different regions in the data. And there you're really combining your physics knowledge with the AI techniques, because you have to know where you expect you have to portion out your data into different regions where you think signals might live, and find other comparable regions where the signal wouldn't live, but you would have background processes that look very similar. And so you're really mixing your kind of physics knowledge of how this should work with your AI knowledge. And what I really like about that method is that it's learning about the signal. So the autoencoder method only learns about the background, but if there really is a signal in your data, this other method will learn about it, and that can help you. Then you can try to interpret the model and see what did this model, if it found the signal, what did this model find, and you can interpret that in the model, and then it can help you figure out what the signal is.
Very, very interesting, and this is happening at Atlas as well, this unsupervised machine learning. So this seems to be something that people are doing more and more. Yeah,
so I'm very hopeful that this will become much more popular in the future. I know that in CMS, we're working on, there's more people working on these techniques, and now that we have this first result, so hopefully it'll become more popular. And Atlas, of course, had actually several results before CMS, so they've been working on this too. And I think a really interesting direction that these techniques are going is doing this in real time. So,
excellent. You've gone to the next question without me even saying anything. So I guess if you can do this quicker, you can do it more cleanly. You can identify things quickly and strange things. If you can do this quickly, you can look for these things as they pop out in the data. You don't need to keep these monstrous data sets and then filter them down later. You can kind of do this online, if you will, while the collisions are happening.
Yeah, so essentially the huge problem in all data analysis at this LHC is that we can't save all the data from all the collisions. It's just not possible. So we're colliding, we have collisions 40 million times a second. Our detector has hundreds of millions of readout channels and stuff. That amount of data volume, I think we're producing more data than the entire global internet traffic, essentially. And so you can't save it all. So we have this filtering system that in real time, 40 million times a second is deciding, hey, is this collision looking interesting? Is there anything going on here that we haven't seen before? And deciding, oh yeah, this collision looks like it might be interesting. Let me actually save it. And so that filtering system is like a huge bottleneck to ever discovering anything, right? So because if the new particle produces a signature that doesn't pass that initial filter, you're never going to save it and you're never going to see it. Yeah. And so the traditional kind of filters that we've applied have been based on, okay, we want to find the Figs bosons. Let's go design some filters to go look for that. Yeah. Or just other general sorts of characterizations of look for collisions with high energy or different particle types and stuff like that.
Yeah.
And those are all, well and good and stuff, but we know that there's always signals that we could be missing because we haven't, even put the filter in to find that. So the idea is, can we take these anomaly detection techniques and apply them at this kind of filtering stage so that we can hopefully save some of these collisions? So yeah, this filtering thing is called our trigger. And there's been a lot of work recently of trying to take these AI techniques and as I was saying before, we've actually, particle physics helped develop kind of the technology that enables you to take some, cool AI model and put it on a chip that can actually run 40 million times a second. So, typical industry stuff, they don't care about that. They don't have any applications that need to run that fast and handle, that volume of data at that speed. So particle physics kind of developed this technology, and now we're putting this anomaly detection neural networks on the in these chips to be running on our trigger. And for the first time, CMS is actually this year in 2024 taking data based on an anomaly detection AI trigger. And it's the first particle physics experiment that's ever done that. And so we have, we've been checking the data as it's coming in, and we've been seeing it. And so we haven't done kind of any physics analysis of it yet to figure out what is this thing actually picking up. But I think it'll be really interesting at the end of the year. We'll have this set of kind of weird looking data, and then we have to go kind of figure out is there anything interesting happening in here.
Amazing.
So that's another challenge, but it's really cool that we're able to collect this.
Is that supervised, looking for particular decays, particular models, or is that unsupervised, just looking for weird, if you will?
Yeah, so the trigger itself is unsupervised, just looking for weird. But you could imagine that you take that data stream and then you do a supervised thing afterwards.
Yes,
so
yes.
Maybe I'm looking for this particular model and I didn't have a trigger in place when we were collecting data, but the anomaly detection trigger, could find that thing. And so I'll look for this particular model in that, collection of anomalous things. Or you could do anomaly on top of anomaly, where you're looking for the weirdest of the weird and see if there's anything new in that. So we're still figuring out actually how to analyze these data streams. It's like of these very anomalous events. I think that's something to work on for us to work on.
It's a really, really fascinating area, because like you say, I remember writing a trigger line for my particular decay. I want a couple of particles which have a transverse momentum above this, and if they combine, I want them to add their massive their energy momentum, and it has to make a mass of this, and then blah 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 blah. Very, very simple, very kind of crude cuts. And now essentially you have an AI algorithm that sat there without any specific decay to look for, just looking for strange things. And as you say, it's going to be very, very interesting to see. I don't know, when will you get your hands on that data set to start having a look? When will that be?
Well, so there's a group of people who are looking at it now, just to check that is as it's coming in, does it make sense? Is there anything weird that it's doing? And it all kind of seems fine. But I don't think anyone's really started trying to scrutinize it to look for new particles and stuff like that. I think that's the next step. Probably, but I guess I would assume that the end of the year, when all of the data from this thing has been collected, that people will start more seriously thinking about that.
Amazing. Very, very interesting. I'll keep an eye out for that. So
yeah.
One thing you mentioned, and you kind of really hit the nail on the head there with one of them, is the uses of AI in particle physics leading to advances in the wider community, in the wider AI world. So how could those impact that wider AI community? I guess you talked about speed, right? So this is not something that most people care about. If we want to classify something, if we want to identify someone in a crowd, usually, half a second delay is not a problem for that. But using particle colliders, that is a huge problem. Is that one area where we can feedback and give solutions to the wider community?
Yeah, I think that's definitely one area where that is happening already. And I mean, so the places where you care about these really fast AI applications aren't maybe what consumers would be interacting with on your day-to-day life, right? Your phone, you don't care if it takes 1 second or 10 microseconds. It's like whatever, you're just waiting. But there are applications that do care. So I think there are some self-driving car stuff where you want to react quickly and you want the AI to be processing that data in real time and understand what's going on. I know one really exciting application, the control of fusion experiments. So fusion is like a new type of energy source where it's kind of the improved version of these nuclear energy that we have now. And one of the real challenges of it is you make this plasma that's unstable, and you're trying to control it with all these magnets and stuff, and it's happening super fast. So it's really hard for humans to react as quickly as they need to control the plasma and stuff. But you could have these real-time AI systems that were, in real time, getting in the data from the different sensors, measuring the plasma, figuring it out how it needs to tweak the configurations and stuff like that, so it can better control this plasma.
So you've got another high dimensionality data set there. I can tweak the magnetic field, or I could change the position of it, or I could change this one instead, or I could change both of them at the same time. How do I get all those correlations and dependencies correct? Well, maybe we can use one of these very, very rapid AI models that we've trained in particle physics.
Yeah, exactly. And similarly, people are looking at using these techniques to control the beams of particles. So, as an experimentalist, I work on kind of the beam is just an input to us. The wizards who are running the Large Hadron Collider give us a beam, and we just sit in the detector and see how collect all the collisions and stuff. Yeah. But controlling those beams is actually an art form and black magic in itself. It's very difficult. They have all of these knobs to turn of the different magnets and sort of things, and so controlling that beam is really important and difficult. And so having real-time AI systems help that. And similar beams are used in cancer therapies and stuff like that. So if we can develop the technology to do those sorts of things, it can help the product for sure.
I think we mentioned earlier as well that just the different types of data. So usually, again, we'll come back to our classic example of separating a cat from a dog. That information there is quite dense. If you have a picture of a dog's head in front of you, there's data that's useful all over the page. In particle physics, we might have a track, a couple of tracks, and then just a load of empty space. So we have to deal with situations where we have lots and lots of sparse areas and then very, very dense areas of information that we want to deal with. And those specific applications, those specific use cases that we have in particle physics, then we can apply them back. Like you say, maybe in driving, if you have a really foggy background, maybe you want to pick something out where there's more information. I can't think of an exact use case, but these are particular solutions that we need in our field that then can be fed back as use cases into the wider field. I think there was one that I picked up, maybe a little bit above my pay grade, but these are three-dimensional neural networks as well. Again, we deal with data in 3 dimensions. A lot of people, if you're looking at a picture on a screen, 2D. So immediately there's different types of data that we deal with that potentially we can feed.
And then the other, I guess, interesting aspect is we have these underlying physical symmetries. So, we understand at, fundamental level, based on Einstein's theory of relativity and quantum mechanics, it kind of limits the space of possibilities of what our answer can be, right? Our answer to this particle physics question of how much energy this jet has can't violate conservation of energy, right? And it can't violate Einstein's theory of how particles can't move faster than light, right? So we have these constraints, we have these symmetries that we know our data has to respect. And a lot of times, these are kind of very complicated mathematical things. And can we actually encode those symmetries in the AI? And we have seen that those give gains to the AI. If you can enforce that the AI respects those symmetries and stuff, there's a lot of gains to that. And so this general technique of how do you get your AI to kind of respect the symmetries that your data has is like a very general problem in machine learning. And I think that, there have been particle physicists who have helped kind of develop these general techniques of how you do those sorts of things.
Amazing. So this dog that's running across the road in front of my Tesla can't possibly be moving at faster than the speed of light or something. This was,
That's
so
a very simple example that it shouldn't. It shouldn't be faster than the speed of light. Yeah.
Good stuff. So I want to come on. So we talked about some of these amazing ideas, and they really are cutting edge, amazing stuff. I want to talk about, as we come towards the kind of end, some of the challenges of using more AI in particle physics. So what are some of those challenges? I hear a lot about interpretability. So obviously
Right.
we're physicists, we're not just making some classification algorithm that we want to sell. We actually want to know how it works, how it did the thing, what was the physics that was going on inside.
Right.
Is this a real challenge with some of these models?
I think it is. It's an active area of research of people trying to understand, okay, this AI model is doing better than our physics-based kind of algorithm we're using before. What is it actually doing different? And because our physics problems are actually so structured, we can kind of write down kind of for some problems in physics, particularly for like jet tagging, you can write down the total space of all possible ways to classify the jets, essentially. And then you can figure out where does the AI live in that space. And then you can actually learn some new physical insights of what the AI was figuring out that we hadn't thought of before. So there's been some really interesting applications along that line. And I think particle physics data is a really good testing ground for some of these interpretability techniques because our data is so structured that you can kind of figure out to a greater extent what the AI is doing. And then how much you care about peeking inside the black box, I think it depends a little bit on what the application is. In some cases, the AI is replacing an algorithm that we didn't fully understand already, right? So like we had some rule-based system, but just because you can write down all the rules doesn't mean you fully understand how it behaves in every possible edge case and stuff. It was some of these algorithms had always been a little bit opaque to us. And if the AI is replacing that, you just check that there's, in all the ways we typically check these things, is it performing how we want it to, and all these robustness checks. But there are other cases, like particularly for anomaly detection. The question I get asked all the time when I talk about these people is, okay, if you found something, can you tell me what you found? I don't want to just know that there's an anomaly.
Is it just there was like a power surge in the detector every time?
Yeah.
And it's picking up that as being strange because there's more, pixels lit up or something. How do you know it's a new particle?
Yeah, so for the anomaly detection stuff, we did spend some time kind of in simulations doing examples of, okay, if this particle was living in the data and this was the AI we trained and these are the results we got, can we tell that it was that particle? And you can tell to some extent. We have some techniques to figure out what the AI has learned. But it's also a little bit of a catch-22 is what if we did all those techniques and it doesn't look like any particle, like it doesn't really make sense to us. But well, wasn't that exactly what the AI was supposed to do? Was it supposed to find something that you weren't expecting? Yeah. So we can't, I guess, guarantee that whatever these AI anomaly detection things find will be easily interpretable to us. But I think that'd be a really great problem to have, that we were finding something really weird in our data and we didn't understand
some places to focus on at least, and then go work out what is going on.
So that'd be really a good problem.
What about uncertainties? Sorry, did you want to add something else on this?
No. Yeah.
What about uncertainties as well? So when we're talking about using these algorithms, obviously when we're doing physics, we want to find a number, a mass or whatever, plus or minus 5 MeV, plus or minus 10 GeV, whatever it might be. We want an uncertainty on all of our measurements. Is that harder when we're using these AI-based algorithms to get a handle on those uncertainties?
Yeah, it definitely can be a challenge. There's some cases where you do really want an uncertainty. So if you want your AI model to just take in all of the Higgs boson events and tell you and measure what the Higgs boson mass is with an uncertainty, I think that's a really ambitious use of AI that we don't normally trust it to that extent, where it can just kind of feed in all of those and it can give you the answer and the uncertainties. So normally we kind of let the AI, do some task, but then we have our particle physics knowledge and our statistical analysis that's going to give us the final number with the uncertainty on it. But there are tasks where you do care about the uncertainty from the AI. So actually, one of the examples is this fast simulation case. So that you train the AI on a limited number of example simulations, and then maybe you're generating more simulations, more like it was trained on 1 million simulations, but now you generate 100 million simulations with the AI.
Yeah.
We know there's probably a point where you're not actually getting a new simulation, right? It was only trained on 1 million, so how can it ever give you 100 million? There's actually some extrapolation that it can do, so you can get a larger number than you put in, but exactly how large of a number you can get before you should really not be trusting the AI model. You can frame it in an uncertainty way, like what is the uncertainty on its prediction of this, how often this type of collision stuff happens. And in those cases, I think that incorporating these uncertainty there's versions of machine learning models which should give you kind of uncertainty handles on its predictions, and incorporating those I think would be a really cool direction that we haven't quite gotten there yet.
What about the in terms of the computing power and the data management? I guess if we want to take full advantage of this, we're going to have to get a handle on all of these pipelines and these data flows, and where we're going to keep these data sets. Is this a big challenge? Is this something we need to start thinking about seriously now?
Yeah, so we have been thinking of this general computing problem just because of the amount of data that we're expecting to collect in this high luminosity area. We knew that was going to be a challenge to computationally process no matter what. And the AI models, we think can help in some ways in, speeding up our simulations and stuff like that, but they're also can be computationally costly themselves. Yeah. And so, in some cases, if we want the best physics performance, we need more compute for the AI model and stuff. And a lot of the difficulty actually comes down to these AI models like to run on, specialized hardware like GPUs and stuff like that. And all of our, normal computational resources were regular CPUs and stuff. So now we're seeing a lot of effort of kind of moving towards these specialized hardware things, moving towards GPUs, and actually changing our regular software frameworks to run even the non-AI parts to run on GPUs, and you can get huge speed ups from that. And so it is a big challenge of just being able to handle all of the data volume that we're expecting and running all the algorithms we want to, like AI models. But it's one that we're definitely working on, and I'm optimistic that we'll be able to handle it when we need to.
Very, very cool. Any I know it's probably kind of edge case, but any kind of ethical concerns with feeding this back into the community? Is there in CMS, in Atlas, in the other experiments, any considerations of how these solutions that we come up with could be used when we feed them back?
Yeah, I mean, it's an interesting question. I think in particle physics, it's not something we're normally used to thinking about. We normally think of our role as, pure investigators of nature, and we publish all of our research, and most of it's open access, and so anyone can use it, and we just hope that fundamental knowledge is beneficial to humanity. And there is, of course, with AI though, because it's has so many social implications and stuff like that, there is definitely ways in which new AI technology could be harmful to the world. I think that because at this point, because our applications are so specific, and all the things we're doing are like how to better analyze particle jets and stuff like that, and there has been some, I guess, broader impact to the community. I don't think that we're the ones who have been who would most have to care about our technology's impact in the world. But I think that it is something we should think about and keep in the back of our heads, that if we create something really new and really cool, that we think would actually have broader societal implications, it is something we should think about. But right now, I think that's not been something we've thought about so much.
For now. I've just got two more questions. So what do you think, and you might have already given the answer to this, that how far do you see this going? What is the absolute cutting edge of this currently? Are we talking about more of these online triggers, more anomaly detection? What do you see as the most exciting area, and where do you see this going in the next couple of years?
So personally, I'm very excited about anomaly detection, really because it's a discovery focused technique. So just enhancing the chances that LHC could discover some new particles, which is I think the dream of any particle physicist. And so I think in all these areas, I expect that we'll continue improving. We'll get better at classification. We'll get better at the simulations. We'll see more AI used in the reconstruction chain of how we analyze detector signals. We'll see, hopefully more people using anomaly detection techniques and more of these triggers and stuff. But the other question is, okay, also what's next? none of these, areas that we're applying in AI models was like handed to us by God. Like someone thought, like, oh, we do this thing. Like, what is something new I can do with AI that I wasn't able to do with before? And I think that's in this, ML plus particle physics world. That's always what's on everyone's back of everyone's mind is like, what's the next thing that we're not doing that we could be doing? And so maybe in a few years there'll be a really new, exciting topic that everyone's jazzed about.
Well, I remember I listened to Javier. We've got the first slide of his talk, Javier Duarte's talk at iChat, and I think he said you've got all of these bulbs coming off where AI is already integrated with particle physics, and he said as soon as he made it, the next day it was out of date. This is moving so quickly at the moment that it's basically becoming part of everything we do in particle physics. So maybe next week we'll be back for another talk about the hot new thing off the rack. We will have to see.
Yeah, if I had to guess, actually, I think the one thing we're not using at all is these like large language models. Maybe not at all. There's some small use cases, but like, the chat GPTs of the world, how can that help us do particle physics? I think would be really interesting. Like, could it help us? Could you have an automated language model that would write some analysis software for you or something like that? So you would tell it, I want to go look for this dark matter model. Can you write the code to analyze the data to do that or something like that? I think that would be really cool.
So as in like, can you look at, all of the code base that you've seen before and tell me, look, my decay is also a two-body decay with an intermediate state, and can you write me something that's basically 90% of the way there, and I just tweak it and it's ready to go?
Yeah, so it has been trained on our code because it's all publicly available, and so I have tried asking it specific questions like, in the CMS software framework, can you write something to do this? And it does an okay job. It's not, it has some issues, sometimes it's a little out of date in some of the stuff, but it gets some of the way there. And so I think, it'd be really cool if we could use those capabilities more to kind of to help us analyze all this data, because we have such a lack of person power, even though there are thousands of people working on it. It's really hard.
Really, really interesting. That is very, very interesting. So last question then. What do we need to do as a field? What does particle physics need to do to get the most out of AI? Is this interdisciplinary teams? Is this building connections with the wider AI community? Is this investing in computing resources? Is this having, PhDs that allow that crossover between machine learning and particle physics? Is it all of the above and more? What do how do we get the most out of it?
I think it is definitely an all of the above answer. What's good is that a lot of people who are coming in, young graduate students and stuff, they've seen the power of AI and they want to get involved. So there's a lot of excitement about it.
Yeah.
And what's great about AI actually is that because the field is so new and all of it became popular in the internet age, there's a lot of really good resources out there for learning about how to use these AI tools and all this other stuff. So I was actually mostly self-taught. I was a classic physics major or whatever. Didn't have much AI coursework or anything like that. But there's a lot of good free resources out there, and you can teach yourself and get up to speed. And so a lot of graduate students coming in now often actually have, I would say, in some ways, stronger AI skills than they have physics, skills, just because the physics stuff does not exist online in the same way. And so that's really cool in terms of there's like all these people coming in with these skills and are hungry to apply it to particle physics. I think that computational resources, I think, is, of course, can be a bottleneck, but I think it's getting better. People are recognizing that we need these, and it's really driving development in the field. Something that's always difficult is kind of convincing large bureaucratic collaborations to let AI models, try to discover new things. And so I'm hopeful
we've done it like this for 50 years.
Yeah.
What do we need this for? No.
And there's good reasons to be concerned, right? Like, you don't want, especially if you're putting this AI at the trigger level, if it does something wrong, you're stuck with that data, right? So there's lots of reasons to be careful. But I'm hopeful that,
That's why you've got one trigger line for your anomalous things.
Yeah, exactly. It's not the whole trigger. It's like it's one small part that we're doing for
Yeah.
say the AI triggers. And so yeah, I'm hopeful that people are recognizing the power of it and recognizing that it can be done in a reliable way. And so we'll continue to see that usage.
And I
But
guess
in terms
as
of
you see the positive results, people will get more
yeah,
comfortable with it, and then we can expand its usage.
yeah, definitely. And yeah, I'm hopeful that this kind of interdisciplinary work will also kind of, I think it's becoming more recognized as like a legitimate kind of hybrid field of this particle physics plus AI. But I hope that will continue to kind of be recognized.
I think P5 made a big point of this. So the P5
Yeah.
report is a report basically for US particle physicists for the funders in the US, and it made a big point of saying, look, we need to understand these advances in artificial intelligence, give some room for people to work in this, have those connections into the wider field. This is a very important area that's advancing very, very quickly. So I think everyone has got the message that this is a very, very important field.
Yeah, I think so. And people always just vote with their feet, right? That's the most important thing. And all of many of the young students who come into particle physics now really want to be working with AI. I'm actually helping to teach a school in 2 weeks.
Wow.
That's like for young graduate students mostly, about how you apply AI techniques to fundamental physics. So I'm excited for that. And I mean, we put the signups and kind of like didn't have any registration fee, and I think we got like 400 people, which is pretty big for a particle physics workshop.
It's also very exciting given there's long lead times now between new experiments, the high power colliders. That people can come into the field, gain these skills, and then go out and do other types of things. There's lots of ways you can get into particle physics and succeed. So that's a really nice message, I guess, to leave people with as well.
For sure. And what I really like about this AI stuff is there's a lot of creativity that's possible because it's so new. You have all these new tools and stuff like that. It's really, as a researcher, you can really kind of have an idea and implement it, and show that it's possible, and kind of you have a lot of room to explore. So that's initially why I got interested in it, is essentially like, oh, this is this new tool and it allows me to be creative and think in different ways and stuff like that. So I find it that one of the most rewarding aspects.
You can get in on the ground floor. So get into particle physics right now, all of you people who understand AI. That's what we're saying, and that's what we're sticking to. Amazing. Yeah. I think that's a really nice message to end on. Oz, thank you so much for taking the time. I've learned an awful lot. That was really, really fascinating. Some amazing results. I will make sure that all of your links, all of the papers are in the description for this discussion. Is there anywhere where you'd like to kind of focus people to learn more, to read up about what's going on in this fascinating area?
I'm trying to think of it. I mean, there's been some pretty good.
Are there any more people who can apply to your thing, or is it closed now? Maybe the next one.
I think we have to close it now. Okay. We're actually worried that we're going to reach the Zoom capacity. If you're able to come in person to Berkeley, then maybe you can still come. In terms of where people can read more, I think that probably all the links that you'll provide are good. The P5 thing was good. There's various, if you just search like particle physics plus AI, and there's a bunch of articles from like Symmetry Magazine, CERN Courier, and stuff like that. So.
And I'll link the other discussion we did before with Ben Nachman and Daniel Whiteson. So there's a lot of very cool people working in this field, and we've learned some more awesome things about it today. Oz, again, thank you so much for taking the time. I really, really appreciate it. And
thanks for having me.
It's been a great pleasure. Have a lovely rest of your day.
Thank you.
Thank you, buddy. Take care now. Bye.
Bye.
I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.